Okay, let's start with this session. This session is about measuring RF frequencies and try to detect what kind of device we have. And this down to a level to individually identify devices. Please welcome Boris Danev.
Okay, thank you very much for your attention. First of all, I want to say that this is a joint work with me and my colleague, which is just here down, but he is not able to today. So we will be able both to answer questions, if you have, and I hope you enjoy the talk. Don't be afraid, the name is different of the presentation, but we will be talking exactly about the same things that is originally on the schedule. So what I will do first is I will do some background about device biometrics, which means can we find biometrics about network devices, any kind of devices. And then what is the meaning of hunting the individuality, why do we need this, and so on. Then I will have two use case studies. The first one is about identifying uniquely wireless transceivers. So this work is much more mature than the second one, which is based on rfid transponders. So for the next one, for the second one, we have preliminary results. So if we have any questions or suggestions, we really appreciate, because it might help us continuing better that work. And then I'll have a conclusion. So yeah, let's start. So what are device biometrics? We are trying to identify a component in a networked environment. It can be an operating system, it can be a driver, it can be a physical device itself. Actually a device that emits some kind of information. And usually how we do this, how we try to build some kind of device signatures based on the analysis of the communication with that component or device, with or without the component's knowledge. So the device might know that we are trying to find some unique signature, or it might not know. And this is also commonly referred as device identification, and it spans a broad spectrum of technologies, like wired, wireless, any type of protocols, and so on. And there are a number of different methods that have been suggested in the literature. Here we'll talk about some of them only. We have to be aware about something very important in device biometrics, that it presents two very different perspectives. So the first perspective is the network authority. This can be used by any type of government or any type of network authority try to do law enforcement. For example, law enforcement agencies in Europe, they're trying to identify illegal transmitters and try to, put people in prison or whatsoever. Mobile operators, they have a different goal. They would like to identify cloned cell phones. If you're a network administrator, you would like to identify track problematic hosts. And of course, you can include some other type of protections against identity spoofing and so on. So if you're able to have some kind of a unique signature of a physical device, even if someone tries to spoof the identity by changing the SSID or MAC address or whatsoever, he will not be able to penetrate the system if his physical signature doesn't comply with what you have in your database. So you can think about this as a kind of a really biometrics, but for network devices. So what is the next perspective? It's the attacker's perspective, of course. Then, thanks to this kind of fingerprinting on building signatures, an attacker can identify variable targets, hosts on the network, and this is commonly, you all know very well, commonly used now in a network. It can also be used for privacy violation. So if you're able to build these signatures, we'll be able to track people just by observing the traffic. And we don't need any kind of identifiers or whatsoever to read from the traffic. And we can also use it for protocol compromise. here I mentioned it was a recent work last year or 2 years ago, I'm not sure, Shake Them Up. They built a protocol that is able to establish keys between two devices based on the fact that it's not possible to say which device sends the bits. But if you are able, during that process of key establishment, to recognize which device exactly is sending, then this type of protocols will directly be compromised. So I will not go in more details about this protocol compromise, but if you look at the Shake Them Up paper, then you see that if you're able to identify the device, then the protocol doesn't make sense anymore. So what is the typical scenario of hunting the individuality? So usually we have a fingerprinter that observes the traffic to and from a targeted device, which we usually call as a fingerprintee, in order to find characteristics that distinguish the device or some of its components. And of course, fingerprinting or signature making looks for characteristics in all layers: application, network, link, and physical layers. In the next slides, I'll talk primarily on the physical layer, because this is something that it's believed to be much more difficult to spoof or to change, because it's due to the inherent manufacturing and specification characteristics in the device. So even if you produce a device in the same manufacturing line, it will have different capacitors or different resistors that will influence the way the device transmits information on the physical layer. And usually, as you see on the next slot, these characteristics usually come from implementation problems, or not really problems, just how the system is implemented, and hardware imperfections, which are very hard to actually try to make the same, like clock skews, for example. And there are two main approaches in fingerprinting. One is active, and the other is passive. The active one, you can initiate communication with the device if it's possible, like passive RFID tags. You're able to query the device and see what its response is. Or passive identification, where you just observe how the device communicates with you. And this is usually in wireless transceivers. You can only observe the traffic. Okay, so it was just general background to what is device biometrics, why we are hunting the individuality. And now I'll start with the first case, which is the case of wireless transceivers. So wireless radio specification and manufacturing process are quite complex nowadays. And the previous work has shown that significant differences in the behavior of the physical layer, even within the same specification, from different devices. Here on the picture on the right and on the left is two different wireless cards which support 802.11 standard. And you could see that even if they implement the same specification with the same how to say, delays and delays and timings, you could see the difference. The picture shows actually before the transmission of the packet. This is the part, this work, yeah. The packet at the beginning, this is just the noise level. And then before each packet transmission, we have a ramping up period, which is defined by the specification. And then after the ramping period, the power goes up to full power, then the transmission starts. And you could see that the same protocol specification and on the physical layer actually has completely different signals for these two wireless cards. And previous work has shown that different manufacturers are kind of very easy to distinguish each other just on observing this physical communication at the beginning. So then we decided to go a step further and see, okay, can we distinguish based on these characteristics even identical devices, which are the same hardware, the same model, and same specification. And in the next slides, we will show some results and also some limitations of the approach and also some attacks that we found relevant in this type of techniques. So what is the motivation about looking at identical devices? So we would like to have reliable identity verification of wireless devices for various reasons, like we want to detect illegal transmitters, we probably want to detect if someone has spoofed your MAC address and trying to pretend to be yourself. So it also can be done for device cloning or key compromise. And that's why we decided just to go and dig on the physical layer and see what can be done there. And usually these characteristics, as I said before, they come from just hardware imperfections in the device. So it's very hard for a manufacturer to just make all the devices completely unique so that we cannot just distinguish. It's also like human nature. I mean, we all have different fingerprints, different faces, and so on. So what was our setup? It's just the general picture. So we used for this experiment 50 wireless sensor nodes. These are actually T-Mode Sky sensor nodes. Exactly the same model. We purchased it at the same time, so they're likely to be also from the same production line. We just wanted to make sure that we have more or less the same, exactly the same devices. Then we built a special signal acquisition setup, I'll present in the next slides, to collect the physical data characteristics from each transmitted packet. This process actually is quite crucial. We need to do it in such a way that we are not compromising or adding additional, let's say, noise or signatures in the process, or at least minimize as much as possible. We always add, but at least minimize as much as possible. Then the typical statistical part starts afterwards. We try to extract features from that physical data layer, and then try to compare with features that we have in other identification database. Is it our own device or it's another device? And for that we used 50 identical devices. So are we able to say if it's our own device or it's another one? So that's the generic framework. So the first step is the signal acquisition. Sorry. Actually here you can see our setup in the building. This is the simplified setup, and here is the diagram. All these components here from the capturing antenna, which is this big standard horn antenna. This antenna is specific that it has for indoor environment, has very good capturing and very strong gain, and it's good to use inside environment. Then we have an amplifier. We definitely need to amplify the signal at a certain extent, otherwise we cannot distinguish very well the features. This amplifier is quite critical, so we used a very low noise, ultra low noise amplifier, quite expensive. It costs around 3,000 euros just for this experiment. If you use a normal amplifier, such as one on a device, on a normal device, you're not able to find the small imperfections in the signal. And then we pass through some kind of a bandpass filters, a special also mixer, and we recorded the signals on a high frequency oscilloscope, so that with a really high sampling rate, we're able to see at even the small imperfections in the signal. And this is the setup here. So the signal of all the devices emit. The signals are recorded from the antenna. They're passed through all the filters in the mixers, recorded on oscilloscope and on our laptop. And then we are able to build reference features and test features and try to compare and see, can we distinguish these devices? So what did you use for this? So the 802.11 B protocol defines a ramping up period before transmission starts. So here we have the noise level. Then the signal will gradually, the specification defines a time for ramping up the signal to full power. And then here actually the second part is the actual transmission. And this shape of the physical layer, you see it on each packet transmission in 802.11 device. Why this is in the standard? It's usually for the gradual ramping ensures that there is no spectral interferences within same devices. It's kind of a make sure that we don't interfere that much. So the signal goes gradually powered up and not directly. It's perfectly possible to directly ramp up the signal at the beginning. So we use this part, which it's usually referred to as the transient part, and you extracted some statistical features from it based on different spectral transforms, which I'm not mentioning in the presentation. And the results were quite amazing. After we also trained the system using some pattern recognition classifiers, then we are able for 50 identical sensor nodes to have a recognition accuracy of almost 99 or 100%. So in 99% of the cases, we are able to say if it's node number 1 or node number 50 or 49 or whatsoever that is transmitting at that moment. And this was under the same conditions of the signal. So the nodes were positioned exactly the same distance from the antenna so that we don't interfere in this ramping up signal. So under the same conditions, these features here were distinguishable. Even though if you look on different samples by just visual inspection, you could not see a difference. But the statistical meanings could find the small imperfections inside this ramping up signal. And here, actually, we varied the recognition. This graph shows the false accept and the genuine accept rate for different types for the number of signals that we use to extract the features. So if you use more signals from the device to extract the features, like 40 different packet transmissions, then we had the highest accuracy. As long as you use less signals to build the characteristic features, then this accuracy drops quite significantly here. So this is due to the fact that using less number of signals has more noise. So more we round up average over multiple samples, better the performance is. And these results are also kind of comparable to biometric fingerprint recognition with an equal error rate of around 0.24%. That was our finding, even on identical same hardware, same model devices. So afterwards, this experiment on this site was under the same conditions. So same distance from the antenna, same antenna polarization, so that we don't disturb the shape of the signal. And then we decided to see what will happen if we go over a bigger distance. The initial experiment here was done over 10 meters. So we collected the signals from 10 meters from the sensor devices. So on this one, we decided to see how far we can go. And we used a university parking space, which is like 40 meters distance. So we collected the signals from 40 meters. Exactly the same conditions again. And the accuracy was exactly the same, more or less, within the statistical error. So even with over a very high distance for this sensor device, which transmit around, the maximum is around between 50 and 100 meters indoors, we are able to distinguish which device has emitted the signal. Then we also performed some experiments on the voltage. So we tried to measure what happens because these devices run on battery supplies. What's happening if the battery goes down and to reaching its end level. Then also the shape was consistently unique within different voltage levels. Where we had problems and where the system didn't work very well is when we tried to do on different antenna polarizations. We just tried to vary the antennas of the device between each transmission and see if these features are preserved. And then we could say that from around 10 sensors that we used for this experiment, only 4 were kind of consistently recognized. So if someone is changing the antenna polarization of the device, this has an implication on this shape change here, and then our features were not good enough to say, oh, this is the device 1 or device 2. We are currently exploring other techniques in order to solve this issue, and I don't have results, but they're usually promising that even with changes for antenna polarization, by using some smart statistical training and kernel methods, we are probably able to distinguish even between different antenna polarizations. So that was the part about wireless transceivers, and I'll go forward with the cool stuff, which is RFID tags. Are there any questions at that level? Yes?
What about temperature?
Yeah, temperature, we didn't test extreme temperatures. We tested only on temperature, on indoor temperatures, and there were no differences.
What about how long the device has been running?
Yeah, we also tested on, we ran it like for, usually this experiment was like for 20 minutes, and also for 1 hour, and there was no difference. This is kind of not a problem given the fact that these are low-power devices. The thing, what we didn't test is that these were all the time regular transmissions. We did not test if the device transmits very intensively for some amount of time and then it stops. This we did not experiment in this setting. We just used regular transmissions, 500 milliseconds per packet for 1 hour. We could see some deviations at some moment, but they were not influencing that much the accuracy, plus minus 1 or 2%. Yes?
How much signal do you need? So how much data do you need?
Yeah, so for building one signature, so this is, we kind of varied from 5 to 40. So if you want more, like the best accuracy we get after kind of if you see the graph here, after 30, the accuracy is almost the same, so around, yeah, 30 packets. Yes. Anything else? Yeah?
So what about deterioration effects? For example, over time the electrical components deteriorate and so the fingerprint changes.
What kind of electrical? Sorry, I didn't understand.
The electrical components of these wireless devices over time, they age.
Yeah, they age. Yeah, that's something that we have not tested, overaging. If we use it, I actually intend to do these experiments after 6 months again, and see what happened with the devices. Because we didn't have, in the period of time, it was within 1 week, we didn't have time to see these differences. But I would say that as even human biometrics, these properties will change. Usually in fingerprinting or face recognition, you need to do regular changes, because, yeah, it's like even code will change your, yes. Yes?
This special device, they can identify if it's in the swarm or is it not?
Yes, so the question is this a setting where only one emitter is setting at the same time or multiple emitters? So in the results I present here, especially this graph, is one signal emitter at a time. So we kind of got rid of any noise coming from our devices. Because these devices have a MAC layer, usually it's ensured that at the same time there is only one device emitting. So at that time the experiments are reproducible. If there were, we tested also with the same devices emitting in the same time, and we could capture the signals in the same way, multiple transmitters. We did not test if we have external noise from other, let's say 802.11 or other devices. This might kind of increase the noise levels and might prevent actually fingerprinting in some cases. But as long as we keep with within the same protocol, even if you have multiple devices, the system works. Transmitting at the same time, sorry. Yeah? Other questions? Okay, so that part on, and I actually not completely. Here I want to mention some of the attacks that we measured because, okay, it's very nice. We can probably do this kind of things, what happens if we try to prevent fingerprinting? So we experimented with two types of attacks. The first one was an impersonation attack. So what we did is we decided to do the following. Can we, in some sense, find similar shapes, and by varying the antenna polarization of these shapes to match a device fingerprint, so that we can impersonate that device. And actually the answer to that question, we took 3 different sensors, which were not part of the population of these 50 sensors that we had. So they were 3, again, the same model, same manufacturing. And then we started sending signals to our system with different antenna polarizations. And the results show that if we use here like n equal 5 or 10 signals to build a feature, the system is vulnerable to impersonation by changing the polarization of the antenna of an intruder device. As long as we keep the number of signals to build a feature, the signature, higher than 20 or 30, then the chances became quite low to impersonate the system. But even though this is not an experiment that kind of says, oh, it's difficult to impersonate the system, it's probably possible to build a device that imitates the shape completely and by varying to kind of impersonate a device. The second type of things we did, we tried to see how the shape actually is influenced if you use some jamming, wireless jamming attacks. And there we were able to actually jam the signals at the beginning. And this also prevented fingerprinting because the shape of the signal was changing quite a lot at the beginning. So as long as we have interference with the signal from some other device, this kind of method fails to recognize the device. So this can be used, for example, for an authority to prevent fingerprinting of the devices by sending regular specific signal interference on the channel. And then the last type of attacks that actually we are currently investigating is trying to replay the signals on the physical layer by using some sophisticated equipment. If we are able to replay the signal, then we also can compromise the system. Yeah, questions over the attacks? Yeah?
In replaying the signal, wouldn't you still have to match the antenna polarization?
Exactly, yeah. You have also to match the antenna polarization, use very expensive signal generators that are able to completely reproduce the signal originally at 2.4 gigahertz. And this equipment is usually more than 150,000 euros. So until now, it's with little success for us. But if it's possible to replay this, this kind of will break the system. Okay, so that was the first case on wireless receivers. This was kind of a more mature work that we decided to present. And now we will demonstrate our efforts on actually try to build physical signatures for RFID transponders. What was the motivation of this? Actually, this slide is probably, yeah. So if we're able to do some identification or classification, we will probably be able to detect cloned or counterfeit devices. And we also, if you can build signatures, we probably can complement some security mechanisms, existing security mechanism for authentication, for example. And of course, on the attack side, we can subvert privacy systems at the hardware level. So the goal for us here was to try what kind of physical signatures we can extract from RFIDs using the physical layer. So here I just want to put a small video which I really liked. It was a guy from Holland. Probably he's probably here it's in the group or not. But we really liked his work. So he was able to clone his own Dutch passport, which contained an RFID chip with data. And he was able to present that to a web check-in terminal and get accepted with a picture of Elvis Presley. Okay, so here is the demo from his website. I gave the details so you can go and look by yourself afterwards. Uh-oh. Very nice. Ah, we don't have... Why we don't have a network connection? Exchange with your phone, so...
Go ahead with your talk.
Yeah.
Boris, keep talking. If somebody near the front would be so kind as to load it so that we can bring the video up.
Actually, I think I will be able to put it finally.
No. Okay.
No? There is one. Apparently no. Okay. Sorry. You have the website, so please, you have the laptops, go and check it. Okay, so what Fonjik did is he was able to break the system and go and present his fake GCOP card on the web check-in. So we decided to see, okay, can we do something against this? Of course, if we clone the data, we cannot distinguish which, if it's your own passport or something else. So with my colleague especially, he started implementing and almost completely finished the experimental setup. So we built an RFID reader ourselves, which is just these two generators. One was used to generate the envelope of the signal, to implement I'll show you later, to implement the commands of the RFID reader. And the other one is the carrier generator that modulates and carries the data. Here we can see the transmitting antenna. So our signal from the generators were going to the transmitting antenna, and here we had an eavesdropping antenna. So we were able to record on oscilloscope again the transmission the physical layer of the RFID transponder. So some things that that he had to really take care of was to make everything completely stable, so that we don't have any antenna differences or whatsoever. So we built this kind of a wooden device, fixed. Here it's explained, so that we have all the time, every time we put an RFID transponder, it has exactly the same conditions, so that we don't introduce any signature due to different positioning or antenna polarization or whatsoever. And of course, everything should be non-metallic to avoid interferences. So that was kind of our lab in that time. And here we could just say about the transactions. So the devices respond to two types of commands according to the specification. One is type A and one is type B. Here's a typical wake-up command of the B protocol, the type B. Beginning, the device needs to be powered up for some amount of time. And this ensures that every time afterwards we have a different puppy number, which ensures against anti-collision. And then we have the wake-up command. Here is the data. It's 10% ASK modulated over. And then here afterwards, this part is the response of the device, which contains the puppy and some other modulated data. So how we can build the signature from this? No, sorry, I'll talk about the response first. So afterwards, after we send this command from our fake reader, we get the response of the device, which is in binary phase shift keying, and usually the subcarrier is 16 times less than the carrier frequency, which is around 13.56 megahertz. So this is how the response looks like in more details. Here we have the anatomy of the A protocol. Sorry. So here is a completely different modulation scheme. It's 100 TSK modified mirror encoding, again at 106 kilobits baud rate. And here we see the response of the device. So the response is on-off keying of the data that comes out. And it has the puppy number and everything the same. And every bit starts with defined phase relation to the subcarrier. So what we did afterwards is that, okay, we could closely simulate the RFID reader. So we sent him a standard command. And then afterwards, we decided to vary the frequency of sending the data and also the baud rate. And you can see on the next slide, actually, this you try to see how the device responds to different type of out-of-spec frequencies and baud rates. And here on this slide, we can see some really nice results. So this, on the first graph, we could see the standard command at 13.56 megahertz. It's almost like a real reader. If we have a frequency which is close to 13.56, we observe also a good response, but different timings. We could not see this from this picture because it's not zoomed enough, but the difference between the end of the command and the start of the response from the device changes on different frequencies. If we try to go a little bit out of spec of the frequencies, like 10 megahertz, we can see that the device tries to respond. And actually, some devices will try to respond, others will not try to respond. And actually, their response will be different also. And here on the graph D, we could see the device, one of the devices that actually tried to respond, actually tried to collect, and he couldn't even read the wake-up command that we have sent. So based on this kind of observations on the different timings in the communication with the transponder, we are kind of able to distinguish between our devices that we have. And unfortunately, we have had only 6 different RFID chips on passports. And some of them implemented type A, some implemented type B, and these timings that we observed were kind of a consistent between each different run on the same device. So unfortunately, we need much more transponders and actually different types of devices in order to more precisely categorize how effective is this to distinguish between the devices at the moment. So we don't have really more data than this. Then this is about protocol dependent. So we just emulated the type A and type B protocols and tried to play with the different frequencies. Then another type of experiments my colleague did. We tried to expose the device to different types of completely independent protocol-independent noise or energy. And actually these 3 experiments, one, we just exposed the device to white noise and see how it reacted. We also exposed it to different linear sweeps over different frequencies, and also to some burst of sinusoidal RF energy. And here I'll show you the shapes that we kind of obtained from devices. So these are kind of shapes from type A and B. It doesn't matter on the protocol because it's independent experiment. So here are the kind of shapes that we could see from devices. And they have some interesting artifacts for analysis, like these peaks at given frequencies here, and then kind of almost noise at the end. So we could see these kind of shapes. They look very nice for statistical analysis that we are currently actually performing. And here it's another type of RF energy that we submit to the device, and we could see a different shape of the device. So what our observations currently are that different classes of devices had different shapes once they responded to these RF energies. Okay, so that's more or less everything. on the rfid transponders. Are there any questions? Yeah, it's, so a conclusion, yes?
You only tried passports, so
Yes.
active devices.
Passive devices.
Passive devices.
Passports are passive.
Yeah, they just respond, on some kind of a command. Okay, I will just conclude. So, according to our experience, we could say that passive and active devices exhibit unique behavior due to manufacturing variations and hardware in the hardware components. And such variations are definitely inherent to the device itself, but they're kind of very difficult to extract and to capture. So we need a very sophisticated equipment, high-frequency oscilloscopes, also signal analyzers, and so on, in order to really capture these differences. In some cases, it's not really possible. And this kind of individuality, if we can find it, it can be useful in both defensive and offensive scenarios, as I mentioned previously. So that's everything on my side today.
Okay, I'm going to respond a bit further to this gentleman's question over here. He was asking about the kinds of transponders we've looked at. We've been focusing mostly on the ISO 14443 transponders that you find in passports. I've also looked at the 14443 chips that are, for example, in contactless credit cards and other kinds of systems that I've studied. The reason why here we're focusing primarily on passport chips is we want a wide range of devices that are still in some sense comparable to one another. So we also have data actually taken from some random other kinds of inlays that we didn't even include with our data here, although we've looked at it. And it's because it doesn't really make a lot of sense to compare a serial box to a passport. We want to be able to show our ability to categorize between different devices that are all intended to operate more or less the same. Any other questions? Yes?
Did you try to reproduce your results with different antenna polarizations and try to compute the polarization out so to make it neutral to the polarization of the antenna? We are collecting the same data with only different polarizations, so you can build a match on each one.
Yeah, I understand. So the question is if we can compensate the antenna polarization and try to match again. We have not done such an experiment because for various reasons we kind of assume that it's very difficult to compensate with adding the different polarization. We'll have even if you compensate this with it will add a signature that is not really unique to the device. So we couldn't find a way to add it, to compensate this with the device signature. So that's why it didn't work. Okay?
Okay. Thank you.